Welcome back to Einstein's mechanics. In this tutorial, we are going to continue with the fluid mechanics analysis. So today we are looking at elasticity, a property of fluid called elasticity. So what does it mean? When the pressure on a given mass of a fluid increases, take into consideration the pressure increases, the fluid contracts. Are we good? Resulting in an increase in what? Density. Also, the reverse occur when the pressure what? Decreases. Meaning, when pressure decreases on a fluid, it is going to what? Expand and the density will reduce. In simple terms, what we mean is if we have a fluid like this, let's assume this container is filled with what? Water molecules. And I decide to increase the pressure on this fluid. So I'm going to exert a force to pull, let's say this boundary is what? Movable. So let's assume this boundary is now here, moving to this point, at this point. So the pressure now is increased inside this container. Please follow the analysis. The pressure is increased inside this what? Container, which is going to push the molecules towards each other, and it is going to contract. So the volume is what? Decrease. And as a result, will increase the density. Remember, the mass is fixed. Let's say a 10 kilogram mass, and the entire volume of the container is, let's say, 2 meter what? Cube. Are we good? So initially our density was this 10 on this 2, which is 5. But now as the pressure is what? Increased, the boundary moved down, decreasing the volume and contracting the fluid. So the volume is now going to decrease, let's say up to 1.8 meter cube. And the density is not going to be the same, the fixed mass on 1.8. Since the volume is decreased, the density is going to what? Also increase. Are we good? That's why we say elasticity, when the pressure on the fluid increases, it increases the density. Are we good? Meaning it's going to contract. And the opposite is when I begin to reduce the pressure by taking the force out, this boundary will now come back to its original what? State, or even move upwards. And as such, the volume of the container or the volume of the liquid will be increased to its original state, and the density will now go back as what? Decreased. Are we good? And elasticity is also one of the interesting aspects of what? Fluid. Elasticity, as the name goes, elastic. So for example, we consider this in springs. So let's say if I have a spring this way, the ability to pull the string by a force P will now what? Cause an increase in the length of the spring, and that's the idea of what? Elasticity, or being elastic. So the fluid elasticity refers to the elastic nature or property of a fluid what? Substance, as explained here. So elasticity means how the fluid is going to what? Contract, or going to be compacted. It's going to be compacted, its volume, and also how it is also going to increase its volume when the pressure is what? Reduced. Are we good? And this is an interesting aspect. So the elasticity of a fluid, or the ability to compress, the elasticity often called the compressibility. Because if the fluid is not elastic, you can't compress it. Assuming this container, this fluid is incompressible, how would I compress it with this force? It won't be okay for me. So the ability of the fluid to be compressed shows it what? Elasticity. Are we good? So, described by the Mach modulus, what makes a fluid compressible or elastic is its Mach modulus. So, In objective questions, you can be asked, elasticity is related to what? And it is related to the fluid bulk modulus. Are we okay? The bulk modulus help the fluid to be what? Elastic. Let's pay attention to that one. So we can say elasticity, EV, of what? A fluid is real. The density, change in pressure, change in what? Density. An interesting equation. Or you can use negative the volume, change in pressure over change in what? Volume. This is the equation for the elasticity of a fluid. I hope with this explanation we've gotten the property elasticity of a fluid. Don't worry, we'll solve questions under that. Another aspect that we have to consider for a fluid is the speed of sound. How best sound can travel through the fluid, being it a liquid or a gas. The speed of sound. When disturbances are introduced into fluid, they propagate in the form of what? Waves. In the form of waves at a finite velocity. The velocity depends on the compressibility. That means we can also say the velocity or the speed of sound, since it depends on the compressibility, also depends on what? The elasticity of the considered fluid. So before we try to make or travel a sound through a fluid, we must also consider its elasticity, the ability of the fluid to be compressed. And this is also further related to its bulk modulus. So the bulk modulus of a fluid is very important in what? Analysis. So the velocity or the speed of sound through any fluid is called the acoustic velocity or the speed of sound. And so in objectives, you can be asked, it is called the acoustic velocity. And it's defined as, so to calculate for the speed of sound through any fluid, C is related to, remember we said it's related to the compressibility, which is the elasticity, EV, and the density of the fluid. So the square root of the elasticity on the density makes the speed of what? Sound. So can we say a higher elasticity means a higher speed of sound. So the more elastic the fluid, the more the speed can travel. Are we good? Since elasticity is also related to the density, as the density of the fluid increases, the speed of sound will also be decreasing because it's inversely what? Proportional to it. What about temperature? You know, other factors that will affect the speed of sound is what? Temperature. Temperature, pressure can also affect. It will affect pressure. So let's consider temperature. How does temperature affect the speed of sound? Are we good? So temperature is proportional to the speed of sound. So as temperature increases, the speed of sound through any fluid, or let's say liquid fluids, also what? Increases. Are we okay? So this is the effect of temperature on the speed of sound. It is used in many applications, and for example, during the blowing of a trumpet in the day and in the night, with temperature analysis, we can see how fast and how best the temperature or the sound will move through the gaseous fluid, and if the fluid is through the sound is through a liquid fluid, we can also indicate. So if I have a container, two containers with water molecules, and this is 60 degrees Celsius and this is 10 degrees Celsius. So assuming a large volume of these two containers, meaning the speed of sound will travel very fast in this fluid as compared to that, because the temperature is higher than that, and speed of sound is proportional to its temperature. Are we good? Let's consider viscosity of a fluid. How viscous a fluid is. Most of the fluid analysis calculations will be based on this viscosity. So you pay attention here. Viscosity. The ease with which a fluid flow indicates its viscosity. So viscosity in simple terms is how best a fluid what flows. Are we good? And from our initial episode 1, we saw that the flow of any fluid is related to its shear stress. We saw that shear stress causes flow in liquid and in what? Gases. Not the normal stress. Not the normal stress. We saw that the normal stress causes what? Deformation. Whilst the shear stress also causes what? Flow in liquids and gases. So viscosity, if we want to know how or the ease with which a fluid flow, then we have to consider its viscosity. Are we good? And it can be, the shear stress is also proportional to the time rate of what? Strain. Yes, anytime a body is stressed is likely to also what? Undergo strain. And we are saying for a fluid, so a fluid moving through, let's say, an open pipe, the rate or the shear stress is proportional to the time rate of the strain. So the strain, the V on what? The Y here is proportional. So the larger the shear stress, the more strain, how deformed the fluid is going to be. Let's put it in simple terms. If the speed, let's say the speed, remember the shear stress will cause greater deformation or greater speed as the liquid moves. And as fast as it is moving, the deformation is severe. Do you understand that? The deformation through the pipe is severe when there is more deformation or when there is more what? Stress. Therefore, as you increase the stress causing the flow, the deformation is also going to what? Increase. That's why we are saying it is proportional to the time rate of strain. And this is the formula. You pay attention to this formula because we are going to use in the problem solving. So shear stress is proportional, and if we proportional to this is the strain, and if we turn this to an equal to, we introduce a constant which is the viscosity of the fluid. So how viscous the fluid is will now determine its shear and its deformation. So this tau is the shear stress, the V is the velocity of the fluid, the Y is the distance measured from the wall. So if this is the boundary or the wall, the Y increases from here, and we are going to analyze that. The V on the Y is the rate of what? Strain, which is the velocity gradient normal to the wall. We will analyze all this, but pay attention to the formula, and I hope we get why this formula. The proportionality factor, which is the mu, the viscosity, is called the dynamic or absolute viscosity. It is a property of the fluid, and it differs from a particular fluid. It is different from each fluid. Are we good? And here we are saying this mu can be called dynamic or absolute viscosity. We have other types of viscosity, and we are going to tackle it in the next slide. And I hope you are enjoying the lessons. Keep following. So the other type of viscosity is, let's look at this scenario. Therefore, viscosity may be defined as the ratio of shear stress to the velocity gradient. From the previous slide, we saw shear is equal to mu, which is the viscosity dV on dy. Therefore, if we are interested to find the viscosity of a particular fluid, it is related to the shear stress on that fluid on the strain, the rate of strain, and we are good to get our viscosity. So this is the viscosity formula, the absolute or the dynamic viscosity. Are we good? All right. And the SI unit of viscosity is Newton/second per meter square. Are we good? Or Pascal second. And it's very interesting. We will be using it for calculations. Are we good? So let's consider the velocity diagram. Now, consider the velocity distribution next to a boundary. As shown in the figure, the following observations can be made. So let's assume we have a boundary. Forget about the diagram. So let's say fluids, water molecules are moving through this drum or pipe. We are going to make some observations here. The velocity gradient will be smaller with distance from the boundary. The velocity gradient, which is the rate of strain, will be smaller with distance from the boundary. Remember, as there is a flow through this pipe, there is going to be, this is the boundary, and remember, it says the smaller the velocity gradient, because y will be from the boundary up here. That's the y. And what we are saying here is that the velocity gradient is greater at the boundary, and it is getting smaller along as we increase the y. Are we good? So the velocity gradient be smaller with distance from the boundary. That's what it means. That the rate of what? Strain is going to what? Decrease as this increases. Remember, if there is a flow through this, the flow is severe, or the shear stress is severe at the bottom, so it will be moving at a faster speed. So mostly when you see river flow, mostly there is high speed at the bottom of the flow, and that's why we are saying that at that place the deformation, the shear strain, the V on the Y is greater, and as you move on top, you may think there is no motion in the flow, but when you dive inside that water, you see that indeed there is speed at the bottom. Are we good? Therefore, the maximum shear stress occurs at the boundary. So this is an objective question. The maximum shear stress for flow occurs at the boundary. So at the boundary here, you can see that for any point you choose, the dV on the y here will be greater and will be decreasing along the line. So here represent the boundary is greater here, and it will be decreasing because as it increases, it will be approaching a straight line, and the derivative or the gradient of a straight line will be what? 0. I hope you get why we are saying it gets smaller from the boundary. The fluid viscosity or velocity is 0 at the stationary boundary. Velocity causes or viscosity causes the fluid to adhere to the surface, and this is known as no-slip condition. And what we are saying here is, look at this pipe is a stationary what? System. So at the boundary, the velocity will be 0 because the fluids at the boundary will assume the velocity of the boundary. And the boundary is not moving, meaning those fluids will be attached to the boundary, and that condition for fluids to be attached to the stationary boundary and no movement occurs is called the no-slip condition. Are we good? That's what we call the no-slip condition, because the boundary is stationary, you are not moving, so any attached molecule of water is also not going to what? move. And this is interesting for viscosity and for flows. The other type of viscosity is what we call the kinetic or kinematic viscosity. Kinematic viscosity. Remember, we have the absolute, and what? The dynamic, which is denoted by what? Mu. But here, there is a special one also called the kinematic viscosity. And the kinematic viscosity is defined as what? That the V, you may think is normal velocity, but this is kinematic viscosity. It is related to the dynamic viscosity or the absolute viscosity and the density of what? The fluid. Are we good? So anytime the kinematic viscosity is equal to the absolute viscosity over the density of the fluid, and its unit is meter square per what? Second. Are we good? So pay attention to the two types of what? Viscosity, dynamic, and what? The kinematics. It will be confusing if you don't pay attention to them. And let's look at how viscosity varies with temperature. If we have two fluids, so let's say this is water, this is porridge. Excuse my spellings. And this is the molecules inside. Obviously, we see that, or let's assume this is oil, grease. Yes, a grease or something very dense. We can see that the viscosity will be different, and the ease with which the fluid flow won't be the same. So if I pour water on the ground to be affected by shear for their movement, the movement won't be the same as if I pour downwards a porridge or a grease, an oil, a very dense oil, because of their viscosity. Are we good? Then we want to check this with the temperature. What if this same water at different temperatures, what happens to its viscosity? The viscosity of a gas, we talked about liquids, so let's consider gases. Are we good? So let me say something small about the liquid fluids. For the liquid fluids, as you increase the temperature, the viscosity is going to what? Decrease. So temperature is inversely proportional to what? The viscosity for fluids, liquid fluids. Let's be specific. Liquid fluids. Temperature is inversely proportional to the viscosity. So if I start to heat this porridge, the viscosity is going to what? Decrease. And as the temperature comes down, the viscosity now increases. What about gases? Gases do not obey such trend. The viscosity of a gas now increases with temperature, meaning for gases, as you increase their temperature, the viscosity then begins to what? Increase. That's very interesting. Are we good? The variation of gas viscosity with absolute temperature can be estimated with the Sutherland's equation. So one scientist called this Sutherland brought an equation relating to the viscosity of a gas and the temperature, because this is somehow not the normal trend for liquid fluids. As you increase temperature, the viscosity also increases. So we have what we call the Sutherland's equation, which is the third equation we are seeing now for gases. So with this equation, we can determine the viscosity at a particular point we want. Are we good? But before we do that, so U is the viscosity we want, the dynamic viscosity we are looking for at a specific temperature given. But before we do that, we must get a reference what? Viscosity and a reference temperature to be able to compare the viscosity of the liquid that we also want. So this mu naught will always be a given viscosity. at a given temperature T naught. So to be able to determine the viscosity at a specific temperature, there will be a reference point, which is a liquid with a known viscosity at a known temperature. Then you use it throughout the equation. So this U is our unknown viscosity. This mu naught is our known viscosity. This temperature is the temperature at which we are looking for this viscosity. And this T naught is the temperature of the known viscosity. S is what we call the Sutherland's constant, and it's different for various gases. We will solve example in the next section using this equation, and we'll see how best we will understand that. It's very interesting, and with that you can also make very good analysis. Are we good? So as I was saying, the viscosity variation with temperature, this is how it looks like. For liquids, we saw that for liquids, this is temperature T against viscosity mu. As you increase the temperature of liquids, the viscosity decreases. But for gases, as you increase the temperature, the viscosity also increases. So there are two different approaches. And we saw that the Sutherland's equation help us with what? The viscosity of what? Gases. So we should also get an equation which will help us for the analysis of viscosity for liquids. And yes, we have it here. The viscosity of liquid decreases as temperature increases. An equation for the variation of liquid viscosity is also given. So this is the other equation we are going to use to predict the viscosity of the liquid. So those Sutherland's ones are for gases and this is for liquid. We will solve more examples with this equation in the tutorial problem solving episodes, where C is constant, B is constant. This C is a constant, this B is constant. This temperature is the temperature at which we are looking for the viscosity. So it will be given. Then straight away we can find our viscosity. Pay attention to the diagram and make sure you understand why it happens that way. The last thing we'll be talking about is the Mach number of a fluid. What does it do? How does it affect us? So the Mach number is the ratio of the speed of the flow, that's the V, to the speed of sound, C, in the fluid. So in simple terms, our Mach number M is the velocity of the flow. As the flow is ongoing, the velocity, the speed at which it is flowing, and the speed at which sound will travel through this fluid gives us what we call the Mach number. And the criteria for considering the gas as a constant density is when our Mach number is less than 0.3. It helps us in many flow, supersonic flows, hypersonic flows, and this is a very interesting property in fluid mechanics. As we advance, will help us a lot in making analysis. And don't worry, we will talk much about it in the other episode. We'll be solving more examples. Follow the episode correctly and you will not miss any information in fluid mechanics. Thank you for watching this episode. Watch out for the next episode and problem solving. Subscribe to the channel, share to friends that may also benefit from this episode. Thank you.